Look at the gap between Europe and Africa across the Strait of Gibraltar. At its narrowest, the distance separating Spain from Morocco is exactly 14 kilometers. Without traffic, you could drive across that span in about 30 minutes. We have already built structures that dwarf this distance. China operates a bridge spanning 55 kilometers. The Eurotunnel connecting the UK and France runs for 50 kilometers entirely underwater. Yet this tiny gap between continents forces an immense volume of physical traffic to squeeze through a very tight space. Roughly 100,000 ships navigate this exact stretch of water every single year. This map shows exactly what that bottleneck represents for the global economy. 33% of the world's oil and gas, 50%. A physical railway or road connecting these shores would drastically reduce the cost of moving goods between the continents. It would directly integrate the massive manufacturing and energy sectors of Africa with the consumption markets of Europe. The financial incentive to connect these two landmasses is astronomical. The distance is short, but for over a century, every single engineering project designed to span this gap has ended in failure. The earliest attempts bypassed traditional bridges entirely. In the 1920s, German architect Hermann Sorgel proposed a physical merger of the two continents. His plan involved building a massive network of hydroelectric dams across the Strait of Gibraltar. By blocking the Atlantic Ocean, the Mediterranean Sea would slowly drain, reclaiming enough land to physically walk from Europe to Africa. Sorgel's plan never materialized. Engineers returned to a more grounded approach. By the late 1970s and 80s, they began surveying the obvious, direct 14-kilometer path, known as the Canyon Route, to build a standard bridge or tunnel. Compared to the 180-meter-deep English Channel, the Canyon Route plunges 900 meters. Bridge pillars here would need to dwarf the Burj Khalifa. Furthermore, the seabed is packed with breccia, a porous, crumbling clay that would instantly collapse under heavy drills or concrete. Above the crumbling floor, the water itself is violently unstable. The warm Mediterranean Sea collides with the freezing Atlantic Ocean right at this juncture, creating severe surface winds and unpredictable oceanic currents. Beneath this lie the African and Eurasian tectonic plates, grinding directly against each other. This active seismic zone experiences regular tremors. Engineers faced a 900-meter drop into crumbling clay, battered by high-speed currents, atop an active earthquake zone. Any structure built on this 14-kilometer route would be shredded. American architect Eugene Sui proposed ignoring the sea floor entirely. He designed a 2-mile-long buoyant tunnel tethered below the surface, avoiding the tectonic plates, surfacing at a man-made island. But inventing entirely new floating infrastructure was estimated at $10 billion. The idea died before a single cable was laid. By 2005, research teams realized the direct route was a dead end. They shifted their focus to a path slightly to the west. This map traces the new path, known as the Threshold Route. It doubles the distance to 28 kilometers, but the depth maxes out at only 300 meters, running along a harder rock seafloor. The blueprint featured a massive tri-tunnel railway system. Once active, travel time between Madrid and Casablanca would drop from 12 hours to just 5.5. In 2006, the Spanish and Moroccan governments put the project to a bid. A Swiss engineering firm won the contract. The project was heavily funded and greenlit to begin construction in 2008. The science checked out, the new route bypassed hazards, the money was secured. Humanity had engineered a solution. Right before drilling commenced, the project collided with a barrier that engineering couldn't drill through: the cities of Ceuta and Melilla. These are two coastal territories located directly on the North African landmass, completely surrounded by Moroccan borders, but they are fully controlled and governed by Spain, a remnant of colonial-era rule. In 2008, the King of Spain visited these disputed territories. The Moroccan government was furious. In direct retaliation, Morocco pulled its ambassador out of Spain and froze the tunnel project indefinitely. 12 years later, in 2020, Spain allowed a rebel leader operating within Western Sahara to enter Spain for medical treatment. Morocco interpreted this as Spain actively supporting rebellion within its borders, entirely shattering diplomatic relations between the two nations. Today, major global powers, including the US, the UK, and China, are applying heavy pressure on both nations to resume construction. The global supply chain relies too heavily on this choke point to leave it vulnerable. The blueprints for the Threshold Route are finished. The tunneling technology exists today to dig beneath the strait. But before a single meter of concrete can be poured under the ocean floor, Spain and Morocco have to figure out how to work together above it. The waterway separating southern Spain from the northern tip of Morocco is one of the busiest maritime trade arteries on the planet. Tens of thousands of cargo ships pass through this narrow corridor every single year. Look across the water from the African coast, and the European mainland is clearly visible. The physical distance between these two continents is incredibly short, roughly 9 miles. We live in an era of unbelievable engineering. We have successfully constructed continuous overwater bridges in other parts of the world that stretch for more than 100 miles. And from the shore, the Strait of Gibraltar looks placid. It appears to be a standard, easily crossable channel of water. Curious. So, given the technology we possess today and the massive economic incentive to link these two markets directly, why is this specific 9-mile gap completely empty of human infrastructure? The confusion comes from how we naturally look at maps. When we view the Earth from a flat, top-down perspective, a narrow blue strip looks like a simple line to cross. But treating this strait as a two-dimensional waterway ignores the extreme physical threats hidden just below the surface. The moment you drop beneath the waves, the illusion of a shallow coastal shelf vanishes. The seabed here immediately drops off into a massive, steep-walled underwater canyon. The trench reaches depths of nearly 900 meters. To build a bridge, engineers need to anchor solid foundation pillars into the bedrock, and at that depth, the requirements become physically impossible. This diagram shows the true scale of that depth. If you placed the tallest building on Earth into the center of the strait, the tip of its spire wouldn't even break the surface of the water. You would need to build something substantially taller than that just to reach the roadway. Erecting a freestanding support pillar of that height in open water simply exceeds the limits of human material science. The sheer weight of the concrete and steel required would cause the structure to collapse under its own mass before it ever reached the top. But even if you could magically materialize a 1,000-meter pillar, the water filling this trench isn't standing still. It acts as a highly aggressive two-way river. Looking at this cross-section of the water column, you can see a thick top layer of cold Atlantic water continuously rushing eastward into the Mediterranean basin at high speeds. Beneath that, there is a deep layer of hyper-salty, incredibly dense Mediterranean water churning violently westward back out into the Atlantic. When you place a static object into that environment, you generate immense shear force. You have two massive bodies of water, millions of tons in weight, constantly pushing against the exact same pillar in opposite directions. Even if a supermaterial existed that could support a 1,000-meter underwater tower, these violent bidirectional currents would shear it in half almost immediately. Yet the water column isn't even the primary reason a bridge hasn't been built. The final physical limit lies beneath the trench, in the bedrock itself. This 9-mile gap sits directly over the Azores-Gibraltar transform fault. It is an active planetary scar. This map shows the tectonic reality of the region. The Eurasian tectonic plate is actively colliding with and grinding against the African plate. The shortest route between Spain and Morocco puts any potential bridge directly in the crosshairs of this volatile boundary line. Bridges rely on absolute rigid stability at their anchor points. Connecting a static, inflexible megastructure to two enormous landmasses that are physically moving independently of one another guarantees structural failure. Attempting to balance a multi-trillion-dollar bridge directly over an active intercontinental earthquake zone turns a massive engineering challenge into an exercise in guaranteed self-destruction. Despite these absolute physical barriers, the economic demand to connect European and African markets continues to grow. Since spanning the abyss from above is impossible, and building through the violent water column is structurally fatal, engineers are looking in the only remaining direction, completely beneath it all. The current working alternative is a deeply bored subterranean high-speed rail tunnel, conceptually similar to the system that already connects the UK to mainland Europe. But the scale of this proposal dwarfs existing systems. Boring through solid bedrock far enough down to safely bypass both a 900-meter deep trench and an active tectonic fault line makes the project exponentially more complex and expensive than anything ever attempted. We've grown accustomed to the idea that modern engineering can pave over, blast through, or build across any geographic obstacle on Earth. But the empty 9-mile stretch of water between Europe and Africa stands as a permanent, humbling reminder that on a planetary scale, there are still physical limits nature simply will not let humanity cross.